Hello, math humans. We're going to be talking about section 1.4 today. We're going to be talking about functions. So the first things that we're going to be concerned about is a set of data, a relation or a function. Then we're going to talk about function notation, and then we are going to evaluate functions. All right, as we begin, we just have some vocabulary. So the first word that we want to talk about is a relation. And a relation is just simply a collection of data points. That's all it is. So it could be a table of values. It's just a set of data. If that set of data is a function, then the x values must be unique, which means that the x values can't repeat. The y values, on the other hand, can be anything. And the reason that that is true is because we're concerned about the vertical line test. So vertical line test. Okay, and again, this is something that you learned in previous math classes, but if I have a set of points that looks kind of like this, and I run vertical lines through that relation, if there is only one point of intersection, then that means it's a function. The reason that it's a function is because the x values are unique, noticing that none of these x values are repeated. The next vocabulary word that we want to use is domain, and that is the set of x values that are defined in the function. And remember that x values are the independent variables, just to make sure that we remember that lovely vocabulary. And the range is going to be the set of y values that work for that particular function. Alrighty. There are several different ways that we can represent functions. So if we want to represent functions, we can do it a variety of different ways. We could talk about a function verbally. We don't often do that, but it is something that we could do. We can talk about it numerically, and oftentimes that would be like a table of values. Okay, the third thing that we might want to do is talk about it graphically, and that's kind of handy. We like looking and talking about functions graphically. And then the last one would be talking about it algebraically. Alrighty. So let's jump right in with our examples. Let me scoot the page up so you can see. For our first example, it says test for functionality. That's a cool word. And we want to do it graphically, and we want to do it, put an and, algebraically. All right, so our first part of that, we're going to have two different equations. It's going to be x squared plus y equals 1. It's not in the form that we like to see. We like to see our equations in terms of y, so I'm going to solve for y. This is a negative x squared plus 1. Well, that's great, because now that tells me that this is just a cute little parabola turned upside down, and it has a y-intercept of 1, so it looks like that. So if I were to do the vertical line test, yes, this is a function. So I'm going to write function. Okay, and then I'm going to do the second one. So this one really doesn't have an algebraic application, because from here I can jump straight to the graph. For the B part, you'll have a negative x plus y squared is equal to 1. Again, it's not in the format that I like to see, so I'm going to solve for y. So y squared is x plus 1. Y is equal to plus or minus the square root of x plus 1. Algebraically, That's telling me that my x values are not going to be unique, so this would be my algebraic application. I guess then that would mean that this is also the algebraic equation. But if I do this graphically, you can put it in your grapher if you choose to, or you can graph it. It means that this particular graph, the square root of x, has been shifted 1 unit to the left. We'll talk about that in a little while. But there's what the graph looks like. And then notice if I do, let me use a different color pen, if I do my vertical line test, it's a failure. So I'm going to write not a function. Okay? And if you were to look at the table of values for each of those graphs, you would see that some of the values for x repeat. All right, so the next thing we want to talk about is function notation. And again, at the beginning of the book, we have just a lot of little topics that we are kind of rushing through that are a review from Algebra 2. When we're talking about functions, x is the input and y is the output, okay? And so the notation might be y is equal to the function evaluated at x. Okay, so that might be some notation that you can see. All right, so let's do an example. This is example 2, and it says we are going to evaluate a function. All right, so let's talk about the function. We're going to be given g of x is equal to a negative x squared plus 4x plus 1. This is our function. X is the input, g is the output, or y. So I want to evaluate this function at several different values. I want to do g of 2, and I want to do g of x plus 2. Okay? So let's just start with g of 2. This is a function. So I'm going to evaluate that function in 2, which means this, the input, goes into everywhere there's an x on the right-hand side of the equation. So this is a negative 2 squared, 4 times 2 plus 1. And if you do that math, you get that g of 2 is equal to 5. Okay? That was actually really easy. So now let's do this one. If I want to evaluate g of x plus 2, this is now the input that goes into this equation everywhere there's an x. So this is going to equal a negative x plus 2 squared plus 4 times x plus 2 plus 1. This is going to give me a quadratic because it's raised to the second power. I can't leave it like this because this is not standard form for a quadratic, so that means I have some math to do. So then I'm just going to move my equals over here. I'm going to leave the negative for right now. If I expand a binomial, I square the first term, multiply those two guys together and double it, plus 4x, square the last term, distribute here 4x plus 8 plus 1. Now I'm going to distribute the negative, so this is a negative x squared minus 4x minus 4 plus 4x plus 9. I combine those two, and now I'm going to combine like terms. These two cancel, so I'm going to get a negative x squared, a negative 4, and 9 is a positive 5. And I would report g of x plus 2 is equals. And notice I put, this is what I did, and this is the solution at the end of my work. All right, the next example, example 3, woo, look, we got the pink action going on. It says find the values for which f of x is equal to 0, which means where does y equal 0? That's what it means in short layman's terms. Now I want to do this analytically. Oops, spelled that wrong. A-N-A-L-Y-T-I-C. There we go. Whew. Anytime you see the word analytically, that means you need to do this algebraically. That means you can't put it in your grapher and find it graphically. You have to do it by hand. We're going to do a couple of these. So the first one is going to be f of x is equal to a negative 2x plus 10. And the problem said find the values for which f of x is equal to 0. So I'm going to say negative 2x plus 10 is equal to 0 because that's what we're actually doing. A negative 2x is a negative 10. X is a negative 10 divided by a negative 2, which is 5. So I'm going to write x is 5 for my first one. The second part of this example, we're going to have f of x is equal to x squared minus 5x plus 6. I'm going to set this, the output, equal to 0. X squared minus 5x plus 6 equals 0. It's a quadratic, so there should be two values of x that are going to give me a 0. Gotta have a little break from Starbucks. All right, so what I'm going to do to solve this is I'm going to factor. I'm going to do guess and test. I'm looking for the factors of 6 that will subtract or add to give me 5. The negative says that the signs are going to be negative. Positive says that both of the signs have to be the same. So this is going to be an x minus 3 and an x minus 2 is 0. The reason that we do factoring is we solve the baby equations. Technically, these would be my two baby equations, and I would get x is 3 and x is 2. The expectation is at this level of math that from right here, once you see the little baby equations, you can jump to writing the solution. So at x is equal to 3 and at x is equal to 2, y is equal to 0. And in case you haven't heard me say it, factoring is your favorite F word. All right, for our next example, example number 4, it says find, let me scoot the paper down so you can actually see it, find the values for which f of x is equal to g of x, and our favorite word, analytically, which means do some algebra, okay? So we're going to do equation A, and let me see just if my notation is good. Yep, we have two problems. Sometimes I don't always have a brain, so I have to check and make sure. F of x is going to equal x squared plus 1, and g of x is going to equal 3x minus x squared. So what this means is I want to find the value or values of x where these two equations are equal, right? That's what it says right there. So I'm just going to set these two little guys equal right off the bat. X squared plus 1 is 3x minus x squared. I'm going to combine like terms. This guy moves over, so I have x squared plus x squared minus 3x plus 1 equals 0. Anytime you have a quadratic or a higher degree polynomial, you need to have everything on the left-hand side so that hopefully you can factor. And I get 2x squared minus 3x plus 1 is 0. I'm going to factor by guess and test. So I'm going to write a 2x and an x. And then I need a 3 in the middle. So 2 plus 1 is 3. Both signs need to be the same. So I'm going to make this a minus 1 and a minus 1. So I get x is equal to 1/2 and 1. So when x is a half and x is equal to 1, these two equations will give you the same value. The second part of this, B, we're going to have f of x is equal to x squared minus 1. And then, where'd my equations go? There it is. And then for g of x, we're going to have a negative x squared plus x plus 2. All right? So it's the same thing. I want to find out what x values are going to let these two have the same output. So I'm going to do a negative x squared plus x plus 2 equals x squared minus 1. A negative x squared minus x squared plus x plus 2 plus 1 is 0. And I have a negative 2x squared plus x plus 3 is equal to 0. I'm going to factor this one by by the AC method, and different books call it different things. I use guess and test, but I'm going to do this one by the AC method. Before I start, though, he's a problem child, so technically I'm going to multiply both sides of the equation by a negative 1, and I'm going to get 2x squared minus x minus 3 is equal to 0. To do the AC method, I'm going to multiply a and C, because remember this is A, this is B, this is C in a quadratic formula. So A times C is 2 times a negative 3, which is a negative 6. Now I need the factors of a negative 6 that give me a negative 1, and that's going to be a negative 3 and a positive 2, which is right here. I'm going to rewrite the middle term, so 2x squared. I'm going to write minus 3x plus 2x. A negative 3 and a positive 2 is a negative 1, minus 3. And then I'm going to factor by grouping. So these two guys play together, and these two guys play together. These two have an x in common, and I get 2x minus 3. This has a 1 in common, and I get 2x minus 3. When you're doing grouping, these two guys have to be the same, so now I'm going to factor them out, 2x minus 3, and I'm left with an x plus 1. And so x is equal to 3 halves and a negative 1. All right, so those are the two values of x for which f and g are equal. Factoring is one of those things that is your friend. You need to be able to factor. As you go higher in math, it becomes more and more important. I learned to factor using this method. I learned how to factor with guess and test. This is a method that I learned after I started teaching, that if this is difficult, this tends to be easier. We will do some delta math along the way to practice our factoring, but factoring doesn't go away. It just becomes more and more important. Alrighty, that is it for today. I will see you soon.